Hey guys, I hope you all are doing good. So in the last lecture, we basically covered time complexity in detail, right? So I hope you have a good idea of how time complexity works. If not, then I would suggest that you watch my previous lecture on time complexity and then move on to this one, right? That lecture is super important to understand. And if you understand that one, then this one should be pretty easy. It's basically the same thing, but for memory instead. Right, so let's start with understanding what is space complexity and then we will move on to see some examples, right? So space complexity is basically the total memory an algorithm uses as a function of the input size n. So if you remember in the time complexity, right, we were trying to measure the time, not the exact time, right? We were not trying to measure the milliseconds or the exact time an algorithm takes. We were rather trying to find a way how would the time increase as the input size n increases, right? So what were the different possible scenarios we saw? We saw it could be that an algorithm takes order of one, which is it takes constant time, right? Meaning our algorithm does not depend on the input size, right? It is always going to take some constant time. Other case could be it takes n time, which could basically be a for loop, right? Maybe you have an array and then you input that array into your algorithm and then it reads the entire array. So in that case, it would be an order of n, right? Another possible scenario was order of n square. Maybe it could be a double for loop, right? So once again, what we are trying to see was not the exact time, but kind of a way to measure as the input increases, how would it affect our algorithm, right? That's what we were trying to measure. And in the space complexity as well, we are not trying to measure the exact memory our algorithm would need, right? We are trying to measure how the space would grow as the input size n increases. Let's try to understand what do we mean by this, right? So when it comes to algorithms, right, there are two possible scenarios, two possible things that we always consider. We consider space and we consider time. Right? These are the two most important factors. This is where all the efficiency comes from. For space, by space I mean I need my algorithm to take as less space as possible, right? I need it to take lesser RAM in my when it's running. And when it comes to time, I want it to be efficient. I want it to be fast, right? But the problem is it's not always possible that we have very good space complexity, meaning our algorithm takes very less space and is also very fast, right? A lot of algorithms have different scenarios, right? They maybe work very fast, but they need space, they need extra memory, right? Or maybe they don't need extra memory, but then they take extra time, right? So we call this space and time trade-off, right? Meaning based on whatever algorithm you're making, you need to decide whether you need it to be fast, but you can use memory, or you don't have memory or you don't want to use memory, and then you can kind of it's okay for you to if the algorithm is slow, right? So that is basically why we always consider the space and the time complexity in the first place, right? Even if you're preparing for interviews or lead code problems, you would always consider people talking about what is the space complexity of this lead code problem or what is the time complexity of this problem, right? So it's very important to understand these concepts, right? So once again, time complexity was measuring the time, how it increases with the input size. And space complexity is how would the space or the memory increase, the amount of memory we need increase with the input size, right? So we are basically measuring the extra memory an algorithm needs in addition to the input space, right? So this is in addition to the input. We are not considering the input that we give to a function, right? We don't care whatever the input size is. Maybe it's like a million values or maybe it's like a single input value. We don't include it in our memory, right? We only consider the amount of memory our algorithm is going to need, how much extra storage it's going to create for its performance, right? Or calculations, I can say. So this basically includes data structures, it includes recursion stack, and it also includes dynamic memory allocation, right? By data structures, once again, just like I said, it would basically mean like arrays. It could be linked lists, etc, right? So the basic idea is maybe your algorithm is using arrays, right? Or maybe it's creating linked lists for performing some calculation, right? In that case, that would basically affect the extra memory we need. Recursion stack, I'll try to explain what this means. A lot of functions, if you've already done a bit of coding, recursion basically means calling a function, the same function within itself, right? Which is what we call recursion. And what do we mean by recursion in this case is, just like I explained in one of my previous videos, right? I think in one of my first lectures, I explained that functions create their own stack, right? They create their own stack, or I should say a space, a memory block to store their variables and information, right? But when it comes to a function calling itself in another function, that's what we call a recursion stack, right? And that's exactly, we also measure it when we measure the extra memory space, right? So what I'm trying to say is, when we measure space complexity, we also consider the recursion stack, data structure, and the dynamic memory allocation, right? Don't worry too much about this part. It's totally fine that if you don't grab a bit of these things. I would just suggest try to pay attention as much as you can. The idea of the video is to give you a very clear view of what is space complexity, right? And then I'll show you the examples. When we go into deep sorting algorithms and other algorithms in the future, and we will solve coding problems too, you would slowly start understanding how the time and space complexity is affected, right? So dynamic memory allocation, I think this one is pretty easy to understand. Let's say my input is n, and I create a array size of n for my algorithm, then I can say that that would be a dynamic memory allocation, right? So once again, don't worry too much about this part. Point is that you understand what is the basic concept of it, right? We consider two things. We consider the space complexity, meaning how would the amount of memory my algorithm needs grows with the input size, and time complexity is how does the amount of time my algorithm needs or number of operations my algorithm performs with the input size, right? Okay, we usually don't count the input data, we don't count the overhead, the compiler overhead, and small fixed constants, right? So just like I said in the last video too, right? We're not trying to find the exact equation for the time or the space complexity, right? So it's not like we are trying to create an equation like order of 2n plus 5 kind of thing. This is not what we are trying to do. We only care about the actual value that's affecting it. In this case, it's going to be n. So we don't care about these constants, right? What I'm trying to say is, maybe in your algorithm, you're creating small variables, right? Maybe you created some x value, x equal 10 or y equal 20, right? Let's say you just created these constant values. Point is that these values wouldn't really, as long as they don't affect or they don't depend on the input size, it doesn't really matter. If they stay constant in your algorithm, we are not going to count it, right? So that's what I'm trying to say. Input data is the one that we input. We don't count it in our space complexity. Second is the compiler overhead. What this means is that basically your compiler also creates some space and everything, and we don't count that as well, right? And the third one is small fixed constants. Just like I said, maybe you created some x equal 5 or y equal 10, etc., right? So maybe you just created some small variables. So I hope things are making sense until this point. Last one is the total space is basically the fixed space, which is constants, instructions, etc., right? Because the instructions, the constants, they're always going to take fixed space, right? It depends on the input and the variable space. So actual space complexity is going to depend on the variable space and the input size, right? So total space equal fixed space plus the variable space, which is arrays, recursion, and dynamic allocation, right? So just a quick summary once again, space complexity is the amount of space as a function of the input size n. In very simple words, how much more space would my algorithm need as the input size increases, right? And we measure it in the terms of n. It could be n, it could be constant, it could be n squared, it could be n log n, just like all the possible examples we covered in the time complexity part, right? So now let's look at a few examples for this one as well. Okay, let's take a look at two different examples, starting with the constant space and the linear space, right? So once again, we're just taking a look at very simple examples, right? This will give you a clear idea of how to look at examples, right? So maybe when you come across lead code problems or other algorithms, you would kind of start getting an idea of how would you measure the space complexity, right? So let's try to take a look at the constant space, right? I want you guys to pause the video and then try to understand what this function is exactly doing, right? Okay, so I hope you have done it. Let's try to read what the function is doing once, and then I'll explain the time complexity part, right? So first thing is we declare a variable total. The point of the function is to calculate the sum, right? So the basic idea is given some value n, right? So let's say n is equal to 10. The point is that we basically keep on adding I values to it, right? So starting with 0 plus 1 plus 2 plus whatever the n value is, we will keep on adding until that point, right? That's the basic idea of this function that we are using. But that's not the point. This is just a very simple function. The point is, what is the space complexity of this, right? What do we mean by space complexity again? The amount of space my algorithm is actually taking, right? That's what we are trying to understand. So if you look at this function, right, I have created this constant variable total, right? And I'm using a for loop. Remember, I'm using a for loop. I'm performing an operation, but I'm not creating any extra space now. Except this total, I have not really created any extra memory, right? I can say that we have created this small constant value I, but except this I and this except the total, we haven't really created any extra variables, right? So, but think about this, right? I'm trying to understand this point. Do you think that based on n, the amount of memory the value total needs would increase or not? It wouldn't really increase more memory, right? The int value total is going to take a constant space in the memory. This I value is also going to take a constant space in the memory, right? It doesn't really matter if n is 20, it is 50, or if it's 100. This total and this int I are basically constant, right? And that's the basic point of this function, right? That is why we are saying that it's constant space, meaning it's basically order of one space, right? That's the basic point of this function. So, but if I ask you the question, right, what is the time complexity of this function? The time complexity in this case would be n, right? Why? Because we are basically performing a for loop until n in this case, right? So even though the time complexity is order of n, the space complexity is constant, right? And whenever it's constant, even though there are two variables, right, we still consider it order of one, right, which is constant space. Now let's take a look at the linear example, right? Once again, I want you guys to pause the video and try to understand what the function is doing, right? So if you understand it, the point of this function is to basically create an array, right? Maybe you've been given the task to create a copy of an array, right? So we can use it somewhere else. So you create this function for it, or you create this algorithm for it, I should say, right? So let's try to understand what we are exactly doing. First, we create this array, and then we dynamically allocate memory for it, right? Since we are trying to create this array of n values, we have to allocate memory of n spaces, right? N different integers. Again, what we do is we create a for loop, we assign those values, and then we return the array, right? So once again, think about this, right? I have created this dynamically allocated memory in this function, but the problem is this would depend on the input size. If my n is 50, then my algorithm would have to create a space for 50 different integers. If my n is 5, it would just need space for 5 integers. But the basic point is, as the n is increasing, the amount of memory my algorithm would need to allocate would also increase with it, right? And that is why in this example, we are going to say that this is linear space or order of n. Order of n meaning the space increases proportionally with the input space, I should say, right? So I hope you understand constant space. Constant space meaning I didn't really create any space or memory which could depend on the input. For example, in this case, I just have a total and I have this int I equals 0, right? But these two values, these two memory spaces I created, they don't depend on n, right? They're not going to increase with n. But in this example, I created this dynamically allocated memory and I'm multiplying it, or I'm creating it based on the n, right? I'm multiplying it by n. So in this case, it's going to depend on the n value, and that is why it is called linear space, right? Now let's take a look at another example. Okay, guys. Now let's try to understand the recursive space example, right? So just like I gave in the lecture slide before, right? It's not just that extra space or just the arrays that we create would take extra memory. It's also important to understand that the recursion also takes extra memory, right? So whenever you call recursion stack or you create a recursive function, just like I said, it's going to create a stack for itself again and again multiple times, right? So it's also going to take memory inside our code, right? So we also consider this part. So let's take a look at an example, right? This is a factorial function. Once again, I would suggest that you can pause the video and try to read this function, right? Okay, so I'll try to explain what this function is exactly doing. It's basically doing whatever I give it a value, right? So let's say I give it 10, then it would give me 10 multiplied by 9 multiplied by 8 until whatever 1 is, right? Until 1, it's going to multiply all these values and finally it's going to give me the result, right? The thing over here is it's actually doing it recursively, right? And what do I mean by that? It's calling the function fact n minus 1 again and again. So first this function gets created, we call it, it calls the fact n minus 1 again in itself, right? This fact n minus 1 is going to call itself again depending on the value of n, right? And how it's going to stop? When it sees that the n value is equal to 1, right? It's going to return 1, right? So I don't want to go into too much detail into recursion. I hope you are a CS student and you have a general idea of recursion. If not, I would suggest that you first try to understand recursive functions and how they work, right? But the quick point is, in recursion, we basically call the same function again in itself, right? Just like in this example. What this code is doing is, it's basically doing the factorial. So 10 factorial would be 10 multiplied by 9 multiplied by 8 all the way up till 1. And that's exactly what this function is doing, right? But the point is that even though I have not really created an array in this, right? I have not really dynamically allocated memory of size n, or I have not created an array of size n. Still, what I'm doing is I'm calling this function again and again. And this is what's happening, right? Think about the computer memory, right? Let's say this is the memory. Let's say I have the stack over here. Let's say this entire block is the stack, right? And just like I explained in one of my first lectures, calling a function, every function needs its own stack. So this function is going to first create a stack for itself, and then it's going to create memory again for this call again. So it's going to keep creating multiple stacks for itself again and again inside the memory. And since that's happening, and since it depends on this value n, that is why we say that this is taking linear space in this example. So the answer to this question, or the space complexity of this particular example, would be order of n, right? Just a quick summary once again, right? Point is that we don't just count the array allocation or dynamic memory allocation, right? We also need to consider the function, the stacks being created. In a recursive example, which calls the function itself once again in it, it's going to create multiple stacks, right? And how many of them would be created? It would depend on the value n in this case, right? So if the value is 10, think about this, right? 10, first we call the function with the value 10. In that function, it's going to call the fact again with the value 9, then 8, all the way up till 1. So what I'm trying to say is, inside the memory, we would in total need 10 different stacks for all these fact calls, right? Or calling the fact function, I should say. So that is why this function is basically taking linear space, or I should say order of n, even though we are not really creating an array in it, right? Next one is, I just want, once again, I think it's very important to understand the difference between iterative versus recursive space, right? So let's try to understand this one. In this one, I want you guys to figure out what's the difference, right? How much space is this one taking, and how much do you think is this one taking? Okay, so I hope you have figured it out, but let's try to read this example, right? This is also a factorial function, right? It's basically calculating the same thing as this one. right? All of these functions are basically the same thing. This is the different one, right? But what's happening is that in this one, we have created a for loop to calculate the factorial, right? So the amount of space this one is taking is just going to be constant. Why? I'm not really creating any memory which depends on n. I've created this variable result. I've created this integer I equal 1. These are the two memory allocations I've done. But remember, they don't depend on the value n over here. Doesn't matter if n is 500, 600, 700, or 1,000 or a million. The res and the int I value, they don't depend on this n value, right? That's the important point to understand, right? I have not really created any array. I have not dynamically allocated memory. So the amount of the space complexity for this function would be order of 1, right? Now let's take a look at this function over here, right? This is the same as this one. Now the difference is that this is doing the same thing. However, it's actually doing it recursively, meaning it's calling itself again within the function. And it's going to stop when n is equal 1, right? That's what's happening. So why is this one taking order of n? Why again is this one taking order of n? Is because it's creating different stacks for the same function again and again. So it's going to create a stack with fact and n equal 10, n equal 9, 8, 7, 6, 5 again and again, right? This entire function would have one stack, which is constant space, and then we have space for this res, we have space for this int I. In this case, we have multiple stacks, or I should say call stacks, for this exact function, right? Because of recursive calls, right? I'm sorry if I'm repeating it multiple times, but my basic point is that we are not just counting dynamic allocation or array allocation. We are also trying to measure if we have multiple call stacks, right? If we are creating multiple call stacks which depend on the value n, right? So that is why, even though both these algorithms are doing the same thing, this one will be order of n space complexity and this one will be order of 1, right? So I hope you were able to understand all these examples. Don't worry too much if you still have doubts in these examples. That's totally fine. As soon as we go into in-depth examples of sorting algorithms and other algorithms, I will try to explain their space complexity and time complexities as well. Okay guys, let's talk about this common space complexities and the time space trade-off, right? So the common complexities are going to be order of 1, which once again, just like I said, is the constant space. What do we mean by constant space again? It basically means that it doesn't matter what the input size is, my algorithm does not depend on the input size, right? The amount of space my algorithm needs would not depend on the input. Second one is order of log n. Don't worry about these three as of now, right? They're kind of complicated, I totally understand. When we come across algorithms which use this space or which basically have this space, I will definitely introduce it, right? But just for a quick overview, one of the examples of log n space would be I hope you guys remember I introduced the binary search. I just gave a quick overview of the binary search in the time complexity video, right? So if we create a recursive version of it, that's going to take log n space, right? That's what's basically happening. What's log n once again? It's basically reducing the space by half or by a constant factor every single time. That's what I'm trying to say, right? That's why this space is order of log n. Third one is order of n square. This could mean that basically maybe you are creating a 2D matrix, right? Maybe the input was n and then you were creating a 2D matrix of n multiplied by n storage values, right? And third one could be n cube, which is again that you create a space of n multiplied by n values, right? Don't worry too much when we introduce these examples or when we cover the examples of these space complexities, we will definitely cover them, right? And last thing I wanted to really talk about is the space-time trade-off, right? I already talked about this in the beginning of the video, but the point is sometimes we can use more memory to make algorithms fast. Other times we use less memory but sacrifice speed. right? So depending on you or depending on what problem you're trying to solve, we basically have two options, right? We generally don't, we generally try to do our best to make both things efficient, but it's not really possible, right? So we have to kind of decide what we want to sacrifice. Do we want to sacrifice the space, right? Or do we want to sacrifice the time? That's what we are trying to decide, right? So one option is that I can make my algorithm really fast, but that would mean that it's going to need more memory, right? Second thing is uh, I can make sure that my algorithm does not use any space, but that would mean that it's going to need a lot more time for performing algorithm, right? Once again, we will cover examples where I will try to explain this time-space complexity or trade-off in them. So don't worry too much, but the important part is to understand that it usually happens that we might have to sacrifice any of these two. Right, so that's pretty much it for this lecture. I hope you were able to understand the time complexity and the space complexity in detail. In the next one, we are going to be starting with arrays, right? Also, whatever examples that I've been covering so far, I would really suggest that if you tried them on your own on a C code, I think that would really be helpful, right? That's pretty much it, and I'll see you guys in the next video.